And since our excellent secretariat has supplied me with a just-in-time clicky thingy, I can actually stand in the pink box like they want us to myself. So I'm Lars Eckert, I chair the IRTF. This is sort of the usual status update of what's been happening. This is a long version of the slides I'm going to show at the plenary later too. And I'm very pleased that there's so many in the room. I just want to make sure that you know there's not going to be any network function virtualization on the agenda today. So if that's why you're here, disappoint you here. Anyway, so we are the IRTF, but we do follow the same IPR disclosure rules as the IETF. The reason is that it's very confusing to everybody if we wouldn't, because the meetings are so indistinguishable, especially when we meet during the IETF week. So if you make a contribution, meaning if you talk here or there or send email, and you have IPR and anything that you contribute, you need to disclose that, the usual stuff. So the slides are up. Thank you very much for the speakers to A, get them to me early, and B, not change them at the last minute. That was very helpful. Remote participation, there's various ways today, is even because, so MeetEcho is streaming us, but apparently also ISOC is streaming us, so there's 2 streams. If you want to see which one you like better, go ahead. We have 2 mailing lists. One is a very low volume announce list, and one is a equally low volume discuss list. The second of those doesn't need to be that low volume. People can use that for discussions. This is the open meeting. As I said, this is the agenda. It's pretty short as usual. I have a few slides on what's going on in the IRTF overall, and then we have the 2 applied networking research prize winners who are giving their award talks, 2 of the 6 that we picked for 2016. Dario Rossi first, Samuel Gero second. At some point before Sam's talk, there's going to be a few people from the quick HTTP community walking in because they asked me to put the agenda this way so that they can make it over. So don't be alarmed if all of a sudden the doors open and like 200 people walk in. Right, so state of the IRTF. We have, I think, 10 groups chartered at the moment, and 8 are meeting this week, which is pretty good, especially since I think at least 1 or 2 of those have actually asked for several slots during the week, which we couldn't give them because the week's pretty full, as you know. So almost everybody is meeting this week. There's sort of a few special meetings here. There's a joint meeting between the Software-Defined Networking Research Group, the Network Function Virtualization Research Group, and the Network Management Research Group. So if you thought that NFV yesterday was full, so I asked the chairs to double check what kind of room they asked for this meeting on Friday, because otherwise it's going to be pretty tight. But you should go. This is, has the potential to be interesting because it's really sort of a discussion on what can we do in this shared space on management. There's 2 groups that are on the bottom here that are in the proposed research group phase. One of them is the Measurement and Analysis for Protocols research group that met yesterday. And the other one's the Network Machine Learning Research Group, which also met yesterday. So if you happen to have been at those 2 meetings, I'd be interested to hear from you what you think should happen here. Should we charter them, or are they not on a good track and we should maybe, not charter them? So come talk to me or send me email. Every IETF meeting, the IAB reviews the progress of one research group. This time it's the Gaia research group. That's because they meet here. Usually they have meetings away from the IETF. They meet at ACM Dev and other venues. This time they're meeting in Berlin, and so we're going to review them. This is my personal, always highly controversial status about the activity level in the research groups. I think most of them are actually pretty active at the moment, so there's a lot of green. The ICCRG has been a little silent. However, they have an interesting meeting coming up that you should go to on Thursday, where they basically going to have a panel. So they invited a few key people in academia and in industry to talk about congestion control for 5G. And it's really going to be a panel discussion, so I don't think there's going to be very many slides. So that has the potential to actually be pretty good. Network management is a little bit quiet, but they usually are. They operate more like an academic workshop. And network coding has been pretty silent, and I'm still questioning whether it's time to close them based on not enough activity happening. And we have the 2 proposed groups that I already mentioned. We have an IRTF RFC stream. It is more like a trickle. There's not been anything published since IETF 95. However, there's, I think, 3 or 4 RFCs in the queue at the moment with the RFC editor, so there should be a spike in Korea. Some of them come from the ICNRG, from Gaia, from, I think Network Management had one. So I'm hopeful that there will be some output on the stream. Right, I'm stepping down in March. I've said that like probably a year ago already. So the IAB has sort of started a process of picking a successor. There are 5 people at the moment, Stephen Farrell, Brian Haberman, Dirk Kutscher, Alison Mencken, and Colin Perkins, who are candidates to follow me. I'm very pleased that we have such an excellent pool. I think I would gladly hand the job to any of those 5 and not feel bad about it. This is an excellent position to be in. If you have an input for the IAB who needs to make the decision amongst them, who you would prefer, send email to either the IAB chair at iab.org or Cindy Morgan, executive director at iab.org. The deadline is this Friday, so tomorrow morning and Thursday morning the IAB is going to interview all of these candidates. And so the feedback selection comes to an end. So if you haven't sent the IAB anything, now would be a good time to do so. And all the remarks are in confidence. Right. We tried something new. So we have 2 things that are called Applied Networking Research BLA. The new BLA is the workshop. This came out of the Yokohama IR SG dinner. Hang on, did I actually miss? No, I didn't. I thought I was missing a candidate there for a second, which should tell you that I haven't had enough coffee. So this is the Applied Networking Research Prizes, where we have the award talks later, right? These are sort of my favorite part of the week because you really get good research that is highly relevant presented here. And people always say we should have more of that. The problem is the prizes really don't scale very well, right? You can't have 20 prizes at an IETF meeting, or even really more than 2 is already stretching it. But we wanted to find some other way to engage more with the research community. And this workshop was born out of that discussion. So this was an academic workshop sponsored by the forum, right, for researchers, vendors, network operators, and standards community to discuss emerging research that's applied. And we want to specifically sort of find things that might transition into IRTF or IETF work. So it's academic workshop, it's peer-reviewed. There's open access proceedings in the ACM Digital Library, which was brought up by academics as being important, right? So we are a publication venue. You get a DOE, you get into the ACMDL. It's sponsored by ACM SIGCOM, the IRTF and the Internet Society, and we had corporate support from Akamai, the Cyclops Project, and NetApp. We have full papers, which for a workshop are usually 6 pages or 7, and short papers, which are 2 pages. Both of them are published. For the full papers, we got 17 submissions, we accepted 9. They had a 20-minute presentation slot plus lengthy Q&A allocated to them at the workshop. For the short papers, we basically, those were given 5 minutes, and the point was to advertise the poster about the short paper that we had up in the breaks, and that worked reasonably well. So the short papers didn't really get a whole lot of face time. That's okay for 2 pages, but the ability to discuss with the people over a poster was actually very good. We're planning the next one of these. So the idea is that this would be a yearly thing. And at the moment, we sort of think that we might do the next one of these in Prague next summer. So I think we have one Staki as a PC chair. We also got a lot of feedback from people that were attending the workshop about what we can do better next year. Some of those suggestions we certainly try and incorporate because they, in retrospect, make total sense, and we wish we would have thought of them before this one. So I promised that the call for papers will come out earlier than it did this time. It took a while to set this up with the ACM, and we wanted to make sure that we have all the ducks lined up before we send people a CFP. So there will be a bit more time next year to actually get the paper in and have more of a shepherding process as well. So you can go to the IRTF.org website, ANRW/2016, and the program is up, the recordings are up. Many of the slides are up if you are interested in what happened there. Right. The Applied Networking Research Prize is the second thing that we do, right? And this is the main part of this meeting. This is something that we do together with ISOC. We got 53 nominations for 2016, which was the highest number yet. So I'm very happy with that. We had a really good pool of papers, and it was really tough to actually pick 6. We have a selection committee that's some IETF people, some IRTF people, some academics, specifically people who maybe won prizes in the past, right? We figured if you've done relevant work, you might also be able to help us pick relevant work. We picked 6. At this IETF, 2 of them will talk, Dario Rossi and Samuel Gero. We have corporate support for this by Comcast. They just agreed to renew the corporate support for the next cycle, so thank you very much. Comcast by no means needs to be the only corporate sponsor here, right? If you have work for a company that is, has a budget for funding research activities, talk to Matt and me. I think we'd be happy to add your logo to this slide and to other materials. And having more money allows us to, for example, bring back the prize winners more than once, or bring more prize winners back more than once. Because oftentimes there is actually something that, an engagement that happens, and they have good reason to return, and more money equals more plane tickets, and we can strengthen that. That would be really good, I think. This is also the 5th year anniversary of the ANRP. We just realized this. So we started at IETF 81, which is 15 IETFs ago. And Matt dug out a little bit of statistics, and I dug out a little bit of statistics. So we awarded 26 winners so far, right? And if you are interested in where the papers appeared that we awarded, right? So 8 of them were at ACM IMC. So we really like to award measurement papers. So if you want to get one of those prizes, step 1, get into IMC. It's not so easy, right? But SICOM, NSDI, CONEXT, also sort of the top quality conferences in the field. We have some IEEE security symposiums and sort of various other venues, transactions on networking, journal and special areas of communications, and so on. But there's a pretty strong bias in the selection towards IMC and SICOM, which I think especially IMC makes sense, right? Because everybody loves to look at data and measurements. It's really approachable, and it really also serves the purpose of the prize, which is to inform the IETF community about how the internet works, and measurements do that. Of the 26 prize winners, 13 of them came back on their own money, which is, I think, a pretty good record, right? 4 of them are here at this meeting. 11 came back as a return trip. The community basically said, this guy has started to show up in this working group, and he should come back. We need to do something, or she needs to come back. So ISOC has some of the budget that we have, I mentioned it, right? It funds these return trips, but we can't do it for everybody. And so it's nice that 13 of them spent their own money to come back. So I think that's a really, really good indication. And we got 1 research group chair out of this, which I personally think is the best thing ever. This is showing you a little bit of acceptance rate. So in the year we had this many nominations, we awarded this many awards, and so the rate is roughly 10 to 15%. In 2011, when we started, we had this crazy idea that we would run the selection process for every IETF meeting, which clearly didn't scale. That's why we did it for 81 and for 82, which is why we got 24 and 13 nominations. And then we quickly decided, let's only do this once a year and pick for the entire year. And that's why for the other years, we have the 1 number. So step 1, get into IMC, kind of hard. Step 2, 10 to 15% acceptance rate here. So it's pretty difficult to get chosen, and that's why the quality of the papers is usually so good, right? Because the bar is really high, actually. So I think this works well, and I think we will do this forever, Matt, right? As long as there's good papers, I think we're going to do this. Or maybe we stop when the room's empty one morning and everybody's. Right, and that's the end of my sort of status of the IRTF bit. Any questions about anything I said? Excellent. Barry, are you leaving the room, or are you going to the mic? Are you going to a microphone, or are you leaving the room? Okay. Hey, this is the one person that came to hear me speak. All right, Dario, I think you're up first, right? Come on over.
If I'm staying here listening better, so the audio quality is better. So I'm Dario, I'm professor at Telecom Paritech. This is joint work with Danilo, which is a first-year PhD student. He's just completed his first year. A couple of other postdoc, Diana, Jordan, and Timur at Linz. So this work is going to be on characterizing IPv4 adoption in the Anycast space. And if I were to summarize this talk in a single slide, then it would be this one. So in a single slide, there has been work in the past that aim at finding Anycast prefixes. And basically, the work was mainly about detecting who are the prefixes that are Anycast. So our work brings this one step further, trying to geolocate where those replicas are. In the spirit with the IETF, so I want to mention a couple of things. So one is that anything that you're going to listen to this talk is going to be open source, which means the software that we're using, as well as the dataset. Dataset that we use to gather the publications. So everything that you are seeing, you're welcome to use it if you find it useful. Okay, so the outline of the talk basically is going to provide at the beginning some background on the technique we're using. So the prize is about one paper, which is the Connex paper, and I'm referring to this paper as the foreground, so the main meat of the talk. But in order to you to understand what are the techniques behind, I need also to introduce the background, which is a paper that was published at the Infocom 2015 that introduces the technique. So I need both because the technique is going to be the building block that we're going to then use to scale this analysis to the internet level, performing one censuses, multiple censuses. The data that we were doing in Connex was related to March 2015. And since December, we kept doing this monthly, so new data is coming. Then since there's a little bit more time, and we kept working on that, I'm going to also illustrate a little bit the future work, the ongoing work that we're doing on this area, notably about the study of the infrastructure and evolution, as well as application to BGP hijacking. So the second thing that you should never use is this incombination.
I can do next slide.
So if I close it now, it works. I cannot. Okay.
Yeah,
so I can.
The pink box doesn't.
Okay. The camera will not follow me, right? Okay. So stay here. So basically, the motivation of using Anycast are very simple. So imagine that you got two guys. One is a typical French guy with a typical French cap, and the other one is in the US. So they want to use the same service, and this service happened by chance to be located in the US. Now, there's going to be a thing that you can do in order to optimize the communication. A lot of work is going on at the IETF in order to, for instance, squeeze the delay of the communication. You can try to set up TLS faster, you can try to reuse identifier, you can use persistent connections, you can use initial window 10 to speed up the time at which the bytes arrive. But still there is one thing that you cannot change, which is geography. So if you need to cross the ocean in order to get those bits, and sooner or later you're going to hit something which is the propagation delay. And so you cannot squeeze the Earth, and so the guys that are going to be in US are going to be closer, and the round trip is going to be lower. And round trip, for those who are familiar with congestion control, also correlate with throughput. So the shorter the round trip time, the better in expectation is going to be your throughput. So the only way, can you do next? Thanks. So, and of course, there is an hidden factor, which is money. So this is not only interesting for the user experience, but also because the user experience correlates with the usage of the services by the same users. So there have been independent studies that were purportedly adding delays to queries, for instance, by Google, by Microsoft. And they were showing that even with tiny amount of latencies, like 400 milliseconds of latency, reduce by 0.7% the searches. Now, 0.7% doesn't seem big in terms of engineering. So whenever you have an improvement of 0.7%, you trash it. The problem is that whenever you're having 0.7 less searches by the volume of Google searches, that means millions of dollars. So that's very important, which is why reducing this delay can be very welcome. And the reverse is true also. So whenever you have a speed up, so reduce the delay, you also increase the people that go to your service, and you, in expectation, increase the revenue. Like, for instance, happened to Shopzilla, which is not only correlated to the propagation delay, but also to what we described before in terms of efficiency. So this is basically one solution. If you want to have users that are happier, that are using your service more, then what you do is that you replicate your service. And when you do replicate your service, basically you're doing Anycast. So there are a couple of ways of doing Anycast. One which is very popular right now is application layer Anycast. For instance, think about Akamai CDN current resolutions. And they're working at unicast in the IP world. So basically the way it works is the following. So imagine that you want to find a resource, you go to a name resolution service and asking for that resource. So that resource is going to be x.com, and a client that is asking for the resource is going to receive a specific, that's going to be, it's too animation intensive, and I don't know why this presenter doesn't work. So if I can try a second presenter, that would be great. Yep. So the name resolution service, in this case DNS, will give you an answer. So an IP address for corresponding to x.com that is gonna, yep, wonderful, thanks. So x.com got mapped to an IP address which is x1 for client 1, and the same for client 2 and for client 3. So you're gonna be mapped to different services. Now this is very good because you have very advantages, like for instance the ability of doing a very fine-grained mapping. You can specify the selection criteria with total freedom. You can guarantee connection affinity, you can guarantee fast failover, but there are also disadvantages, which is basically the need to manage this service, which can be complex and ad hoc. So there are very interesting papers about Akamai, about how do they realize this service for the multitude of services they are using, which is why an alternative technique, which is interesting, is to use IP layer Anycast. So in a nutshell, IP layer Anycast is to have multiple servers that are serving exactly the same content, that share the same IP address, which is going to be advertised by multiple BGP point of origin, which means that the BGP announcement is going to propagate in the network. Routers will receive possibly multiple such announces, and whenever clients want to reach that address X, they will just delegate this to forwarding. So it's going to be natively supported by IP, totally transparent to the application. You have some level of tuning. The disadvantage is that you don't have fine-grained control, and BGP metrics are not necessarily performance metric, are more likely tied to economic incentives. Another problem is that it's possibly prone to prefix hijacking. I'm going to comment briefly on that later. And that you also don't have any explicit connection affinity guarantee. So imagine that our routing happens, then a TCP connection can go from one server to another just due to the forwarding process. Our focus is going to be on IP Anycast. So, for instance, think some very popular addresses that everybody knows is, for instance, Google 8.8.8.8. There are also Cloudflare, Edgecast, beyond the classic DNS root servers that are using Anycast. So imagine that you want to geolocate those. Now you go to commercial databases. I'm listing some of the answers that you can get from those. For instance, when you query Google, then you're going to get Mountain View, California. Well, right, that's the headquarters. Close. Then you get New York, New York. Very nice song, but not there yet. Then you also get United States, Max Mind. And moreover, you get United States with a very, very precise geolocation, so that was time varying, independent. And when you go over Google Maps and trying to find where the location maps, it's going to be the geographical center of the United States, which is okay, but you don't have the accuracy. So if you knew that the bubble was possibly over the whole set of the United States, that would be valuable information. Still, you would miss the point, because by definition, with Anycast, you would want to have more than one answer. And here you're just getting one answer. So what could we do? And this is going to be about the methodology that we are going to use in this work. We could use distributed measurement. For instance, this is a tool that is using this launching measurement from multiple places in the world, so United States, Europe, and Asia. Is using traceroute, ping, and other tools. And if you ask to trace one of those IP Anycast addresses, it's going to tell you, oh, look, this thing is happening to be in Mountain View, California, because it trusts commercial database for the visualization. And I'm reaching it in 2 milliseconds from Ireland, which is a little bit weird, because you're going to faster than speed of light. And those that have tried to publish that things go faster than speed of light had to step down recently, right, from the places in applied physics. So in the internet, your equation is going to be 1 millisecond roughly. You can travel about 100 kilometers. And this is due to the fact that you have optoelectronic conversion. You have the fact that you don't walk in a single straight line from Ireland to California, but you follow the coast, for instance. The speed of light in fiber is not like the speed of light in vacuum. You have BGP, so you're not going as fast as speed of light, but you're in a factor of 3 of that. Okay, so implicitly already seeing from this, you could detect, wait, that's a speed of light violation. So 2 milliseconds means that if really this guy from the United States, this guy from Europe, and a guy from China are hitting the same IP address in 2 milliseconds, well, that must be 3 different things. And these 3 different things are Anycast. So this basically, the idea is not new, and this was precisely the tool that was used in NANOG work by Renesys to detect who are the Anycasters. And our work is going to be to raise this to the next level and geolocate where they are. So just to give you a brief coverage of related work. So I'm going to talk about 2 things. One is the technique to do the geolocation, and second, the scaling this technique to all the PV4 space. So in terms of geolocation technique, there are these NANOG work that we already discussed that is using traceroute to just do detection. Then there are a couple of work that manage to do also enumeration, but they are relying on protocol-specific technique. They just work, for instance, for DNS. They are making DNS chaos queries. In the chaos reply, you get some very specific information that is made by operational DNS root servers that is going to convey you the IATA airport code where the Anycast replica is located. So this works only for DNS. So now we're going to leverage this information in order to validate our technique, but our technique itself will not use this information. We're going to just be based on latency probes, as few as possible, so that this technique uses a fistful of ping, so about hundreds of ping are sufficient to do a quite accurate geolocation of the probes. And we validate it for DNS and also for CDN like Edge, Cluster, and Cloudflare, where we had to develop another additional technique to find ground truth. Then once we have this technique, what we can do is that we can analyze what are the deployments of Anycast. Typically, people have taken a quite small set of targets. For instance, most of them were looking at DNS services, and they were studying them with really fine-grained eye. So they were looking at metrics like proximity, affinity, availability, load balance of specific deployments. Our focus is going to be different because we're going to take all the IPv4 space and geolocate those replicas, so we cannot achieve the same fine grain, and we'll mostly gather some aggregate metrics, as you will see. So the workflow is going to be as follows. We're going to first start with the building block, which is the analysis tool. That is going to be fed by large-scale measurement from Planet Lab, from RIPE, in order to extract those things that are Anycast. And so let's start with an overview of the technique. So we do start with measurements taken from multiple vantage points. Since you know, or you're supposed to know the position of the vantage point, then once you have a latency measurement, you can map this to a disk, which is a geodesic disk, which is the maximum distance that this packet can have traveled on the network. And so basically, a set of measurement maps to something like this on a map. Then what you do is that you apply the detection of speed of light violation technique that we saw before. So whenever you have two disks that do not intersect, those two disks are contacting two separate replicas. And our point is that we want to be able to find the largest set of disks that do not intersect, which by definition, each of which contains one Anycast replica. And we do this by phrasing the problem as a maximum independent set problem, which is an optimization problem which is known to be NP-hard. And that's a little bit unfortunate because it means that in order to solve it, it takes time. So what we can do is that we can solve it with the brute force approach for deployments where you have a finite number of replicas, like for instance Planet Lab. It takes some hours. And then we can also use a known approximation, which are greedy approximation, that in all the possible spaces achieve deceiving results. 5 approximation means that you find 5 times less Anycast replicas you could find with the brute force. But in this particular problem, we show that they're practically indistinguishable from the optimal. And the advantage is that you're going to be much faster, so you're going to be much more scalable. Now, the process works as follows. You find all the disks that do not intersect. And so since this disk here intersect, you cannot no longer consider it. Why? Because it may be contacting a replica which is not in the intersection, or it may be contacting one replica which happens to be exactly here in the intersection of either of those two disks. So in this case, it would stop at 3, and this is your number. Still, we are not there at individuate finding in which city are those replicas. And so here we're going to use another criterion, which is going to be a classification problem. And we're going to pick with our maximum likelihood criterion something which is very simple. So we're going to pick simply the largest city in the area. So you're going to trust me with this for one reason. I'm going to show you how the latency disks look like. Basically, 90% of the disks are larger than 1,000 kilometers. The radius of Earth is 6,000 kilometers, so many of our disks are bigger than the Earth. So which basically means these are totally useless. There's huge latency noise, and so in order to filter out those noise, what you do is that you need to take into account something which is a side channel information. And the side channel information in question is pick the largest city. So why is that? We started from saying you want to deploy Anycast in order to ameliorate services for users. So where do users live? In cities. So if you want to optimize for the majority of the user, where you should place your servers? Well, close to where those users live, so close to large cities. Now, of course, when I'm saying that the server is going to be in Paris, it's not going to be sitting in the Opera Paris because the land price is too costly. Okay, so it's going to be in the Paris neighborhood. And given that, in our case, 1 millisecond equals to 100 kilometers, well, we're going to say that this probe is going to be in the vicinity of that city. An additional advantage is that since most of the technique that we can use to validate the approach are leveraging information which is encoded as IATA airport codes, once we pick a city, we can verify whether our classification problem was solved in a correct fashion or not. And so, for instance, in this case, we would be picking Frankfurt because Frankfurt is the most large city in this disk. Then we have another step, which is we have a feedback process in which once we have selected a city, we're going to collapse this disk to 100 kilometers around the city, which means that now the physics of the problem has been modified. So we can go back here having a different set of disks, some of which are smaller, and so, for instance, this disk will not be intersecting with any other. We continue applying the maximum independent set, the classification, and so on until convergence. And this process keeps pretty fast. So at a glance, what we achieve is that we have 75% recall with respect to the ground truth of DNS and CDNs. We have a geolocation which is precise in 75% of the cases, so we are picking the good cities. And the median error in the remaining cases is about 300 kilometers, so which is not huge. It is protocol agnostic, so we just need latency, so we can apply it for DNS, for CDN, for whatever service. We'll see that later. It is lightweight. We are using 100 times less probe than previous work. It is fast. We are doing this in hundreds of milliseconds with respect to thousands of seconds that it require the brute force. And as I told you, the performance are quite close. It is ready, so there is open source to code to measure, analyze, and map. So the code works from RIPE and from Planet Lab, provided you have a RIPE account and a Planet Lab license, you can use that. And there's also an open data set along with the code, which is the one that we use to publish the results. So you can confirm, or even if you want to ameliorate the tool. So now the main meat. So the reason why I'm here speaking is that then we took this technique and we applied it at scale. I'm going to skip about some of those details, but I have a lot of backup slides if you're interested, and you can interrupt me anytime if something is not clear, or if you want any further details. And the main thing that I'm going to talk about here is how do you scale up the technique, and the need to be gentle to do that, so that you can get results that I'm going to quickly scream through. So how does a typical IPv4 census look like? You start from 10 to the power 7 live targets. So this is a EP hit list, which is provided by John Eidman at EZ. And as we see yesterday, these need to be updated quite frequently. In the proposed working group about measurement analysis protocol, there was a talk showing that in the next month after the release of the hit list, if you're just using the hit list, 80% of the target is going to go away. So this is something that you need to update frequently. Then, taking this list, you're taking on the order of 100, so a few hundred vantage points. You do want to avoid overloading targets. So you don't want to send too many packets. You want to be nice. You want also to avoid pinging or contacting guys that explicitly tell you that don't want to be probed. So for instance, those that are replying you with administratively prohibited host network message, then you need to honor those responses. So you ping them once, you put them in a gray list and never ping them again. And you ping them explicitly with the ICMP because it is service agnostic. We also did tests with several protocols. Like once we know that this service is running over port 53 UDP, then we also try it with DNS. Once we know that it's over port 443, then we use over HTTPS. And the results are basically in line. But when you don't know, should you try with port 53 or port 80, then ICMP increases the recall, so you can have a much larger coverage of the internet. Then you want to go fast, but not too fast. Actually, the tool we were using during Connex went at about 10K host per second, so it's not as fast as ZMAP. There is not the point. We want to leverage that from many, many vantage points, so we do want to go at a speed that doesn't harm the host. Right now, we're going in the lab at over 100K, so we're going much faster, but still, we do take all the necessary steps in order to avoid overloading destination. So for instance, we use a linear shift register in order to maximize the inter-arrival time between any two consecutive packets hitting the same guy. And basically, in these censuses, we are running at 1 packet per minute per target. So we are not really pissing off anybody. However, the problem is that since we're sending at 10K per second to 10 different guys, the reply aggregate. So the router, which is close to us, will tell, oh, you're under attack, my God, and it's gonna drop packets. So experimentally, so not everybody, of course, was in this scenario, but we want to increase the recall, and we had time, so the solution was, well, let's slow down, and with 1K packets per second, experimentally, we had much less problem. Which means that our census running few hours. A census is 10 to the power 7, out of which you get some 10 million, million replies. Out of those, some 100,000 ICMP errors, of which some are the gray listing that we saw before, and then you get still millions of replies, on the order of 5 to 6 million, if, depending on the census, on the month, on the week. So you need to run the technique that I showed you before, million times. And now the point is that if you are taking 100 milliseconds per run, then it would still take you more than 1 week to go over everything. So we went back, we re-engineered everything in order to run it under 3 hours. Right now I think we're running in 1 hour, so that we can have the whole process basically continuously running. Now, once you're done so, and you're done with the analysis, what you get is basically only 10 to the power of 3 targets, so /24s, there are anycas. So basically, this is the proverbial needle in the IPv4 haystack. So let's look at how does these addresses look like. So here I'm showing a couple of things at a glance. So this is the cumulative distribution of the number of replicas that we can find over 2 different platforms, Planet Club and RIPE, using a number of vantage points which is reported here. So there are some for which we found less than 5 replicas. They are likely anycas. We manually verified some. We prefer to be conservative, and so in the remaining we focus only on the guys that are more than 5 replicas, which are unlikely to be false positive of any sort. And in this case, you see that most of them we find no more than 20 replicas with RIPE, but that we find possibly also the double with RIPE, even if we are using less vantage point. This is because RIPE Atlas vantage point can be chosen between a much larger diversity. So RIPE Atlas now has over 10,000 probes from many more autonomous systems in many more countries. So we can have much more diversity. So if we make a careful selection of those probes, then we can have a better results. The problem is that even to refine those results over RIPE, due to a number of limitations in the RIPE limiting platform, it still takes days. Well, whereas in Planet Lab we are able to perform a census in under 1 hour. So, which means that these 2 platforms are really complementary. So what we do typically is that we do a census over Planet Lab, and then we refine only over RIPE to consume less credits. Those /24s are pertaining to about 100 AS in 71 cities in some 38 countries with some 10,000 replicas. These were data from March 2015. So what we did is that basically, just because we were giving the talk here, which is a good motivation to improve the thing that you're doing, basically we started performing monthly censuses since December 2015, and now we are exporting those since basically the last month. So right now you can go back in time and see the different measurement, how they look like for any of the IP addresses that we find in the vantage point. So here is just an example. So how does this top 100 look like? Actually, for reason of space, since the screen is too small, it's going to be cut at 50, but you can find the top 100 in the paper. And you immediately see that you find basically all good big fishes. So here what we were doing is that we were probing each /24, then from whois information we were aggregating multiple /24 to a single owner. For instance, here over hundreds /24 belongs to Cloudflare, which is one of the top CDN. And so we did the process iteratively, so to find CDNs, service provider, hosters, important autonomous system, social network, and security companies. So all the big names are there. So basically we found the silver needle in the IPv4 haystack. So we got important ASs, we got people that are serving popular host content. So this is the Alexa rank and Kaida rank. Kaida rank is for placing autonomous system, how important is an autonomous system in the internet topology. And the Alexa rank tells you how much a web domain is popular over the internet. And so you find people that are consistently serving quite a lot of pages that happens to be in the Alexa top 100K, so among the top 100,000 popular pages. You get a lot of service diversity. We perform a complementary port scan exhaustively of 1 target alive in each of the /24 in the census. And so you can see that, okay, there is port 53, DNS, we expected that. There is port 18, port 3, okay, can be expected because there's CDN. And then you can find oddities like Incapsula and OVH, where you have really a lot of ports which are open. I'm going to comment a little bit on that later again. Then you find very heterogeneous footprints. You have people that have hundreds of /24 that are serving anycast contents, like Cloudflare, and you have people that have only a single IPv24 prefix. Okay, which gives you an idea of, if you want, the fragmentation and diversity of the deployment in the space. So which is why we couldn't go and find and consider each of these deployments in isolation because they are pretty different one from the other. So from the complementary port scan that we did, some interesting findings, for instance, like I said, we were doing stealthy scan over all ports, and so we found not only CDN and DNS, but also unexpected traffic like OpenSSH, which is not the typical thing you would expect to find on an Anycast replica. One of the possible reasons that I've been given is that it's basically misconfiguration. You have a server which runs on OpenSSH with default configuration. By default, the configuration SSH is binding to all IP addresses and not only the unicast interface that you should run. But if you have any other explanation, I'm willing to take it, so from an operational experience. Then we also look at the number of open ports. This is a complementary cumulative distribution function, is an ugly plot. To be explained, but just to point out that there are, for instance, over 10,000 open ports in OVH. OVH is the largest hoster in Europe, the third in the world. So there is quite large diversity of services that are served over Anycast. Then we were also doing a breakdown of the software that is running using the Nmap fingerprinted techniques. And we were also trying to correlate how different is the web ecosystem for the Anycast from the web ecosystem from the typical unicast. And the correlation between the popularity of those software is pretty different, meaning that exactly as you do for the DNS, that run a special version of the bind daemon, which is made for root servers, then also the popularity of web services is different from unicast to Anycast. For instance, here you can find things that have been customized by Cloudflare or Edgecast. So these are their own products specifically for that. Okay, so this basically summarizes a little bit of the finding we had in the Connex paper. Of course, there are more details, but I'm not going to go over all of them. I'm going to just want to comment a little bit on how could you use this technique. So we've been using it, for instance, over historic write measurement. You can go back in time and see what was the architectural evolution. And here, applying the technique or looking at the DNS chaos ground truth, so you can see how things did evolve. This is, of course, for DNS, but you can do it for any target that were traced in RIVE. Then, orthogonal to the spatial and temporal dimension, we did another thing, which is taking a look of real passive traffic. So we have a passive probe in several ESP in Europe. We have a list of the targets that are Anycast worldwide. So what we can do is that we can cross-check what is the traffic that a user see with the list of IP Anycast traffic and give this description of those traffic. So this is just an eye candy that shows that even there is a huge diversity of the thing that people see. Just a quick statistic. In the typical day, about half of the users are going to encounter an Anycast service just because some of the popular services like WordPress by automatic is hosted over Anycast. So this is pretty popular. We also find interesting stuff like, for instance, RTP radio over Anycast with session that lasted 4 hours, which is a little bit a comment about the fact that Anycast is pretty stable despite the fact that you have strictly no control over the BGP process, so it can be routed at any moment. But then, since you're using a live radio, well, they should work in practice, right, for the user. Otherwise, they wouldn't be using those services. Now, as a final thing that I want to talk about is our recent work on BGP hijack detection using this technique, not only this technique. I mean, in one slide it's going to be very short, so I'm not going to be able to explain the whole details. I just want to convey some messages. And this is this work is being carried on in the context of a Google Faculty Research Award being awarded last year. So remember that I said that IP Anycast, one of the problems was that you could hijack it more easily. Why? Because basically BGP hijack, you can have multiple points of origin that advertise the same IP prefix. Now, the difference between an hijack and Anycast is whether the routers are authorized or not to advertise this prefix. And there's a lot of proposals for solving this problem, though none are deployed yet. So this can be a problem made harder by the fact that implicitly in Anycast, you would already expect to have multiple routers advertised in this. And so in order to debunk whether this is really Anycast or this is somebody which is trying to exploit this, is going to be harder. So how could we use this technique in order to help in this space? Well, we have basically two ways to do it. So one is having reactive scan on suspicious BGP announces. So you receive an announce you wouldn't expect, and for instance, you issue IGRD measurement on suspicion. Well, the problem is that even though we were doing that, the BGP hijacks are of short duration, so nobody knows exactly whether what is the duration of the hijack. So there are hijacks that last for months, but there are also hijacks that are supposedly be in the order of minutes. Right now, the monitors are exporting BGP information in the order of 15 minutes. Now with BGP stream and other very recent advances, we are moving to the 5 minutes region. But basically, this means that whenever your control plane sees something, your data plane would have seen it like 5 minutes ago. So issuing a measurement now, well, it may not bring any useful information. So which brings us a different perspective, which is, okay, then what about scanning proactively all the /24 prefixes like we're doing now? Of course, possibly with a subset, so with an opt-in mechanism. If you don't want to be pro, just tell us we're going to blacklist you. And if you then change your mind, well, we're going to remove you from the blacklist. And so what we could do is that we can make measurement continuously, store, say, the last hour of censuses made at the frequency of 5 minutes, so that if any time you see something in the BGP control plane, then you will be able to ideally go back in time and say, oh, how does the data plane measurement look 5 minutes ago? Which is basically this Back to the Future service that we are building up and that we plan to make available sooner or later. So the main problem here is that in order to go from hours to minutes, then you need to go much faster than the current speed. The point is that also detection is easy than geolocation, and that we can parallelize the thing, so we don't need to have everybody going to all the nodes in the same time. You want to do that if you want to achieve an exhaustive geolocation, but if you just content yourself with detection, well, you might also get away with parallelization. And also, as I said, the software can run much faster, so we have hopes, to make this service working. So which leads us to the conclusion. So basically, I'll show you one technique to perform accurate and lightweight detection, enumeration, and geolocation of Anycast replicas, which is independent of the service. Then we apply this technique to perform several censuses, which is quite a lot of engineering, and we get some interesting results with expected findings as well as unexpected findings. Whenever you scale something at the scale of the internet, of course, there are many interesting things that you didn't expect that you find. And notably, we find big fishes that are also in popular content, but also with a remarkable service diversity. So for instance, something that we found that I didn't tell anybody because nobody cares any longer about peer-to-peer is that we found also BitTorrent trackers that are hosted over Anycast. So these guys are very good. They're very efficient. Then, I mean, who could else I can tell that technical community like this one. Okay, and as I told you, so we are doing this thing monthly and we are exporting that. So we have gathered good feedback from people that are using the service. So if you have any suggestion on how can we make this more useful to you, don't hesitate either to ask now or to talk me later. So with that, I'm concluding. And then I have a scary set of slides that probably you don't want to go over with, but this is the floor is yours. Now you have time for questions or comments.
Giovanni, SIDN. Great work, Dario. One question. So you use ICMP to probe that, and very often ICMP is also put in low priority delay queues. So how you handle that thing there? Like, because you have the evaluation of light, speed of light thing. But if the packets are put in a queue, which is like kind of low priority, how do you handle that?
Yeah. So I'm gonna probably show you two slides. So one is we already seen. So this is the distribution of the latency, and actually most of the things that we are seeing are in a space that brings you in the size of a continent. So whenever you're above 10 milliseconds, you're already in a radius which is pretty large. So you don't even need to mention buffer bloat. Buffer bloat can go to a space of seconds, which is here, and basically you're in intergalactic communication radiuses, right? So the circuits that are really useful are those that are really, really small. And you don't know how to, this is the biggest problem. So once you find some guys with good connectivity, well, okay. But you know, it's not necessarily easy to find them in advance. And just probably, oh, sorry, this slide, which is useful. Okay, it tells you, it's a little bit different from the question you asked. Basically here we're putting a threshold and we are discarding these that are over a given threshold, okay? Which is basically sort of the same in a mirror fashion. You're asking, oh, what happens if you have disks that are very large because the packets are queued or they're low priority? So basically this is packets that are gonna incur a high latency, and these are basically gonna be factored out in the solution of the problem, because the solution of the problem takes, as you can see, disks that are short, and then even if you start thresholding, even disks that are very large, so these correspond to the size of the Earth, and this is wider than the size of the Earth, then you don't care, because basically in the greedy solution you're gonna sort disk by increasing size, and there are chances that the most useful disks are gonna be the smaller. Then that depends on the geometry of the problem. If you are in a space which are nobody around, even with a very large disk, if you're alone, then maybe in the solution you're going to be picked up. But otherwise, what you rely on is in the existence of this lucky guy that have a privileged path, that are close basically to this replica, they are sitting on the Anycast replica, probably because they are in the same internet exchange point, whatever. So those guys are the one that you want to select with the, as a result of the optimization problem. So the others are just the overhead that you incur because you need to do those measurements, and then once you see, oh, 100 millisecond latency, you're not thrashing it away, but the solution of the algorithm will. Okay?
Thank you. Thank you.
Zhen Cao. So I have a question regarding, because you are using the ICMP to measure the latency. I don't know if you have ever experienced the longer delay because of the buffer bloat issues in the Pi.
Oh, wait a second. Sorry. So as I'm showing here, this is the dataset we are making public. This is the dataset from the Infocom paper. We recently had an extended JSAC paper which export different protocols. Then the censuses were only done with ICMP because it's more lightweight. But here we're using ICMP, DNS, and HTTP. For instance, this one is one of the reasons why Planet Lab is interesting. I couldn't mention it before. So RIPE, you cannot run HTTP measurement because RIPE policies prevent to use HTTP in order to circumvent, for instance, legal barrier in a given country. So you could use RIPE in order to download content which is illegal in your country. So here we were doing measurement with different protocols. And I think I have, so let me check this validation for CDN. I have a validation for a protocol, which is not this one, so this one. So here we have ICMP, TCP, DNS over UDP or DNS over TCP. So you know that whenever a packet reply exceeds 512 bytes, DNS will transmit it over TCP, so you can also use TCP over DNS. And basically, this curve shows that whenever you're trying different services, whenever you're using ICMP, irrespectively of the service, CDN, DNS, well, you're always having the same recall. If you're using different protocols, then you might, for instance, if you're using DNS, well, you only get DNS because Edgecast is not running a DNS service, Cloudflare neither, and Microsoft is replying to your HTTP requests. So if you're using DNS, well, you would lose, okay? So clearly, there is, at a given point, Cloudflare stopped replying to our pings to their internal addresses. But this said, the fact is that, okay, you're gonna have difference, and I'm trying to go back to the slide that I showed you before, which is this one. You're gonna have different protocols, we're gonna have different latency measurement, possibly because they are differently treated in the routers, although it is not the place where buffer bloat gonna be. Buffer bloat was mostly at the edge of the network, so in the access where you have large capacity in front of a relatively narrow pipe. Routers are made to treat packets at line rate, so there you wouldn't expect to find very large queuing delays. In this case, if you're using ICMP, you know that you're going to get 3 times median latency with respect to the speed of light. So this is basically the slowdown you have. With TCP and UDP, you have slightly different figures. There is a recent paper in NotNets by a NS project, which is Internet the Speed of Light, where they're doing precisely so. They're evaluating what is the overhead, or if you want the stretch with respect to light speed for different protocols. And the numbers are slightly different, but basically you're gonna be back into this slide here, where, okay, provided that you don't have huge additional factors, if that factor is still bounded, well, you still get away with exactly the same result. I don't have a picture that is showing the accuracy, and I'm jumping from one slide to the other, sorry. For this, we were seeing that the recall was different, but then once you were running the results over those guys that were replying, for instance, pick TCP for Edgecast, pick ICMP for Edgecast, run iGreedy, do the result match? Yes. So they were perfectly matching with a round index of 1, which is basically the two things are exactly indistinguishable. And the reason being that whenever you are finding guys that are 1 millisecond away, they're going to provide you with extremely accurate. Whenever you find those guys, you're going to find people that are extremely reliable in telling you where the probe is located. If you couple this with the fact that you're not selecting at random, but you're picking larger cities for the criterion that will be given above, then you basically factor out those problems tied to the huge latency noise that, by the way, use ICMP, use TCP, use whatever you want. 90% of your disks are basically trash with respect to the information you can get out of the latency. So you just use latency as a hint, and then you move to other thing, which is basically side channel information, as I was telling before. So I don't know if this convinced you, but...
Last question.
Yeah, Giovanni again. This is all for V4, which is pretty interesting, of course. I was wondering if you, I know V6 scan is pretty hard, I mean, it's pretty hard to do nowadays, the space is too vast. But if you could like reverse DNS, the IP addresses of this V4 you found, and then get the quad A records and run V6, yeah. Have you guys did something like that?
So the software is V6 ready. So it means that iGreedy can work with this V6. So doing the V6 census, that's another story. Okay, so what you mentioned, we try to do it with the reverse DNS. The point is looking for, okay, I have a name, then I'm gonna find A6 records or AAA records, and I'm gonna ping those. And I mean, there are not so many guys that reply, for instance, in the Alexa ranking. So right now, it's not so easy to do it automatically. It is ready, sooner or later we can do that, so the software runs. Then doing census, we didn't thought about it because the scaling can be a little bit different. And still right now, I mean, there are many presentations about, is it everybody reachable from IPv6? So you're adding another source of complexity, which means that, okay, you can try, but you don't know whether it failed due to whatever problem in the midterm. So a couple of years from now, probably it would be interesting to have another try. We have a look at it, but for the time being, we set it up aside.
Okay, thank you.
All right, thank you.
Thank you.
So the second winner is Samuel Jarrow from Purdue, who's a PhD student, fourth year you said, I think, right? Who's presenting his security analysis of Quick.
Okay, yeah. As Lars said, my name is Samuel Jarrow. I'm a PhD student from Purdue University. And today I'm talking about our work on how secure and quick is Quick, a provable security and performance analysis. I should mention that this is joint work with Robert Lechev, who's now at MIT Lincoln Labs, Alexandria Boldriva, and Christina Naitu-Rataru. So I'd like just to take a moment at the beginning here to talk about some of the motivation for our work and really for Quick more generally, which has all to do about minimizing latency. So with proliferation of mobile and web applications and sites, latency becomes a very important issue for the internet, for operators and things like that. We had a couple examples of that actually in the last presentation, but other studies show that even a quarter of a second latency difference in latency can be a significant competitive advantage. And there's one study that even says that, well, Amazon loses 1% in sales for every tenth of a second increase in latency. So this is something that people care very much about, especially people like Google. Additionally, there's while bandwidth today is fairly cheap, it's only likely to increase. Latency faces a fundamental limitation in that we simply can't send information faster than the speed of light. So, unless the physicists can magically solve that for us, or we drill tunnels directly through the Earth's core, or we all move to a smaller planet, we're essentially stuck with a fundamental challenge to minimize the number of round trips times required to set up connections without sacrificing security. And that's exactly where Quick comes in. Quick stands for Quick UDP Internet Connections. So it's built on top of UDP, very common transport protocol in the internet. And it's a communications protocol that was developed by Google and implemented as part of their Chrome browser back in 2013. And the protocol essentially has two primary goals: to produce security that's comparable to TLS, while also providing significantly reduced connection latency. And the questions that we try to answer in our work are, well, how effectively does Quick actually achieve these goals in the presence of attackers? And to understand why this is a non-trivial question, I'd like to compare Quick and TLS along a couple of different dimensions here. The first of these is the time to set up that connection initially. So hopefully we're all fairly familiar with TLS. We use it all the time for online banking, for Facebook, for essentially anything else encrypted on the internet. But TLS is actually built on top of TCP. So when you set up a TLS connection, you're actually going to set up a TCP connection first with a handshake involved in that. And then you'll set up your TLS encryption keys and then begin to exchange encrypted data. By contrast, Quick basically combines those two stages into a single handshake, which results in significant latency savings. Now, of course, to do this, Quick relies on UDP instead of TCP, and TCP provides some handy benefits for protocols like this. Things like reliable delivery, in-order delivery, some protection against connection spoofing. But of course, it also, as we see here, adds latency, and there's some performance availability attacks like the TCP reset attack that are known against TCP. So the question then comes, well, what about Quick? They had to re-implement all of these guarantees that TCP provides. How effective are they at getting that latency? Are there similar performance attacks against Quick? Then to the second dimension that I'd like to talk about here, which is how TLS and Quick begin to exchange their data. In TLS, we have a fairly simple picture. We start with establishing our session key, and then we can use that to begin exchanging data. Quick, on the other hand, is much more complicated. It actually looks like it takes distinctly longer to begin to send encrypted data. However, we can actually start to send that data before we have our final session key set up using this initial key. And the benefit of doing that is that we can often avoid one RTT in that initial key establishment by caching some of these parameters, achieving the 0 RTT connections that's Quick's goal. But of course, this more complicated handshake then raises the question of, well, what implications does this actually have on the security of the protocol? Okay, before I go further, I'd like to mention some closely related prior work on Quick at CCS a couple years ago. This work developed a security definition for multi-stage key agreement protocols like Quick, and showed that Quick's key exchange meets that definition. They showed how they could modify Quick to compose it with secure data exchange protocols and prove that this modified version would have been secure, which is important and valuable, but we also, there's a couple questions that are left over from this work, which is, well, what about the security of the protocol as it actually is today? And then how can attacker impact these latency goals of Quick? And these are both important questions because Quick isn't just some academic protocol, but is actually deployed by Google in the internet today. And these turned out to be exactly the questions that we address in this work, which is what provable security guarantees does Quick provide and under what assumptions, and then how effective is Quick at actually minimizing this latency in the presence of attackers. And just to give a quick highlight of our results, we developed a security definition suitable for performance-driven protocols like Quick and prove that Quick satisfies that definition. However, Quick does not satisfy the traditional notion of forward secrecy provided by some modes of TLS, like TLS DHE. Forward secrecy, just as a reminder, is this notion that if a server becomes compromised at some point in time, then connections made to that server prior to that point are still secure, cannot be compromised. And turning to our second point, we've discovered that with some simple attacks on some of the handshake parameters, we can actually prevent Quick from achieving these minimal latency guarantees. And we demonstrated these attacks to show that they are in fact practical. Okay, so in this rest of this talk, I'd like to spend some time talking about our provable security analysis of Quick. We'll then probably spend the majority of the time looking at our performance degradation attacks. And then I'd like to quickly mention a little bit of related work on TLS 1.3 before finally concluding. So turning to the provable security analysis, before we get into too much detail, we need to understand the way Quick's protocol actually works a little bit better. So in Quick, we have our client and our server. To begin a connection, the client generates a connection ID, just a random 64-bit value, and sends that to the server. The server generates an STK, or source address token, which is tied to the client's IP address and is used to prevent IP spoofing, and sends that back to the client along with an object called a server config, which contains information about the supported encryption algorithms of the server, as well as a public Diffie-Hellman value for that server. When the client receives this message, it verifies the signature on that server config, generates its own set of Diffie-Hellman values, and sends all of that information back to the server, which verifies the source address token is correct, hopefully preventing IP spoofing at that point. And then both client and server can compute an initial encryption key based on the Diffie-Hellman values from the server config and that the client generated, and use that to begin securely exchanging encrypted data. At some later point in time, typically very shortly thereafter, the server generates an ephemeral session Diffie-Hellman value, sends the public value to the client. They both generate a new final session key and use that for further data exchange. So there's a lot of details here. The really important part to get here is that the SDK and the server config can be reused, which means that if a client has previously talked to a server before, they can do an abbreviated handshake where they just generate a new connection ID, reuse the SDK and server config as long as they haven't expired, generate their Diffie-Hellman value, send that all to the server, everything works from there. Essentially what we've done is we've just saved a full RTT off the beginning of this connection. And in fact, because we can generate that initial encryption key from just the server config and the server's the client's Diffie-Hellman value, we can actually achieve 0 RTT connections where we start sending encrypting data without having heard anything back from the server yet. Of course, there are also a couple other complications with the QUICS protocol here. In particular, the client is unable to check the authenticity of this source address token value. It's just an opaque string of bytes to the client, which means that if this is ever corrupted, maliciously or otherwise, then we get an inconsistent view of the handshake, and the client and the server establish different encryption keys, which is a problem. Additionally, if the server is compromised before the server config expires, then data that's encrypted under this initial key can be revealed, can be compromised. This is the forward secrecy difference that I mentioned earlier. So we developed a provable security proof or analysis for QUIC. It's not the only type of formal security analysis available, but it seems it's very popular for protocols like this in the community. And basically what this means, how we went about doing this, is we developed a protocol and environment definition, who the entities are that we wanted to model, how they communicate. We then built a security model which defines what the attacker is allowed to do, if there are multiple attackers, whether they can collude, whether they can corrupt entities, whether they're allowed to only observe or to observe and modify the communication, and what the attacker has to do to be considered successful. So are we only interested in attacks on confidentiality and authenticity, or we also consider attacks against denial of service, IP spoofing, things like that? From these two components then, we build a proof by reduction, which proves that the attacker can succeed with only negligible probability under reasonable assumptions on the building blocks of the protocol, the digital signature schemes, block cipher schemes, and so forth. As you can probably guess from that description, this is a very dense analysis, very notation-rich, very complicated. I'm not going to bore you all by presenting all the details here. What I'd like to do instead is to just talk about some of the complications that we faced in this analysis, and then present the main security result. So probably the biggest challenge that we faced in doing this analysis was that prior analyses of TLS, of which there's a large body of work here, are not suitable for QUIC. It's very relevant work, but it's not suitable for QUIC because in QUIC we can begin exchanging data before that final session key is set, which is not possible in TLS and not supported by all of these other analyses. I should mention that there are newer analyses of TLS that came out after our work that may be more suitable for that, for analysis of QUIC, but that obviously didn't help us when we were developing this. Another challenge that we faced is that parties can set distinct different initial keys in the QUIC handshake, which means that the traditional notion of having a matching conversation to capture data privacy isn't sufficient, and we need this new notion about setting a key with an entity to be able to capture that. Also, as mentioned, the server config is public and can be reused before it expires. That means we need this weaker notion for forward secrecy for these initial keys, where the keys are completely secure once the server config that's used for them has expired. However, the traditional notion of forward secrecy still applies for the final session keys, so we're still good there. And then finally, UDP does not address unordered delivery of data or spoofing. which means Quick has to implement all of that itself. And we'd really like to, and did include that all into the security model that we built, which means we need to be able to capture all of the different complications that involves. Okay, so to address all of these, we developed a new protocol model to capture data exchanges with these multiple keys. We call this the Quick Communications Model. We built a new security notion, Quick Authenticated and Confidential Channel Establishment, based on the notion used to prove the security of TLS. And from all of that, we established our security model, and I can present our final security result, which is that Quick meets our notion of security here if the underlying signature scheme is strongly enforceable under chosen message attack, and Quick supports two well-known signature schemes. Quick note, we discovered that neither of these schemes have been proven to be strongly enforceable. They have been proven to be unforgeable, however, and we believe our proof could be modified such that that would be sufficient for Quick. More details about that are in the full version of our paper. We also need the underlying authenticated encryption scheme to be indistinguishable under chosen plaintext attack and authentication secure. And Quick uses AES and Galois counter mode, which has been proven to provide these properties. We also need a couple very standard security assumptions, that the strong computational Diffie-Hellman problem is hard, and the random oracle model for the HVAC and the key derivation process. So provided all of these things are true of Quick, then we can prove and did prove that Quick is secure. Okay, so that's the provable security analysis of Quick part. The performance degradation attacks is what I'm going to talk about next here. We found basically two classes of attacks against Quick. The first relies on replaying public cacheable objects, things like that server config or that source address token, which ultimately results in fooling the client and the server into believing that a connection is making progress, such that they waste significant time and resources trying to continue that connection. The second class of attacks that we found operates by manipulating unprotected packet fields, which ultimately leads the client and the server to have different views of the handshake and compute different encryption keys, at which point everything fails. Both classes of these attacks are smarter than simply dropping packets or delaying packets because they're harder to detect. And they also confuse clients and servers into believing that the connection is making progress, such that both parties waste significant time and resources, computational and memory, on these connections that will never succeed. Ironically, these attacks also stem from the parameters whose very purpose was to minimize latency in the first place, the server config and source address token particularly. And finally, and most importantly, these attacks do not concern data authenticity and confidentiality. So these are only attacks against the protocol's performance or availability. Any data actually exchanged by Quick is unaffected, and we've just proven that Quick is in fact secure. Okay, so these are the 5 different attacks that we found against Quick. We targeted the Quick Chromium implementation from a couple years ago, which was current when we started this work. We implemented these attacks in Python, leveraging the Scapia library. The really important thing to take away at this point is that these attacks can be used to deny clients access to any application served over Quick, and then they cause the servers to waste significant resources, time, and memory for keeping state. I don't have time to talk about all of these attacks in detail, but I would like to talk about just 3 of them here to give you a flavor of what these attacks are like. So the first attack is the STK manipulation attack. STK is this source address token that's used to prevent connection spoofing, IP spoofing. In this attack, we've got our client, our server. Our client generates a new connection request and sends that to the server, which generates this STK value that's tied to the client's IP address and sends that along with the server config back to the client. Unfortunately, there's an on-path attacker in the middle of the network, and what this attacker can do is he can modify that STK value, just change it to some other value, and send that to, forward that on to the client. The client then attempts to verify the server config signature, which succeeds. The server config is genuine and unmodified, generates its Diffie-Hellman values, sends its reply message back to the server, which is again intercepted, and our attacker replaces that its malicious STK value with the original one, which is important because the server will immediately attempt to verify that. At this point, the client and server then compute their initial keys. Unfortunately, that source address token is used as part of the input into the key derivation process, which means that they compute different initial keys, and at that point, they can't exchange any, they can't decrypt any of the exchange data. And this attack is made significantly more powerful because once those initial keys are established, essentially all messages that Quick exchanges after that point will be encrypted. So any error messages that might clue the parties into the fact that this connection is horribly broken can't be decrypted and are of no value. As a result, what ends up happening in this case is that the connection will wait until an idle timeout occurs before being abruptly terminated. That takes multiple seconds at the client side and actually multiple minutes by default at the server side. Until that happens, this connection is stuck in a hung state. The second attack that I'd like to talk about is the server config replay attack. In this attack, again, we have our client and our server. The client generates a new connection request, but there's this attacker that's in this network that's listening for these connection requests and generates a spoofed reply to that request way faster than the legitimate server actually can, because the attacker is closer. And this spoofed reply contains the genuine server config for the server. Remember, the server config is public cacheable information, so it's easy for the attacker to get it either by snooping prior network connections or even contacting the server directly. The attacker also places a fake randomly generated STK value into this message and sends that to the client. The client again verifies the server config signature, generates its Diffie-Hellman values, and tries to talk to the server, where predictably the STK that the attacker supplies fails to verify. At this point, then, these clients already established their initial key. Clients already established their initial key, so all messages they send are encrypted. And any error messages from the server that could correct the situation are actually rejected because the client thinks it's already received the first message from the server, so it throws them away. And again, it takes an idle timeout to eventually terminate this connection. The third and final attack that I'd like to talk about is the STK replay attack. In this attack, our client sends a connection request to our server, and the server sends the usual reply message with the server config and source address token. However, there's an attacker in this network who's sniffing for these response messages, grabs that server config and STK value, and begins spoofing lots and lots of connection requests from this client. And this works because that STK is bound to the IP address, but is reusable while not expired, because we need that for the zero RTT to work, which means that the attacker can legitimately spoof all of these connection requests from the client. And for each of these requests, the server is going to need to derive keys for them, it's going to need to keep state, and it's going to need to send reply messages, which means that the server quickly falls over. I actually demonstrated, or was actually able to demonstrate this against the Quick server that's part of the Chromium implementation. The server actually ran out of all of my RAM and swap, and the out-of-memory killer eventually killed it. Okay, so it turns out, interestingly, that these attacks against Quick actually have some similarity with prior attacks that we know about for TCP and TLS. One example is that this STK replay attack that we just talked about has a lot of similarity to TCP SYN flood attacks in that both attempt to overwhelm your server with essentially connection requests that are then abandoned, that the attacker has no intention of ever using. A traditional mitigation against this is, of course, single-use SYN cookies, which essentially punt the state for an RTT from the server to the client. That's somewhat the idea of the STK value, but unfortunately, the STK needs to be replayable for 0 RTT, which means that the attacker is still able to spoof a very large number of these connections using it. Additionally, the manipulation attacks that we found show similarity to SSL downgrade attacks, which is an attack against older versions of SSL where the attacker rewrites the handshake messages to request older vulnerable crypto algorithms. Protection was actually introduced in SSL 3, and this basically includes a hash of all of the handshake messages in the very final message and checks that the client and server compute the same hash. Obviously, if an attacker rewrote the handshake messages, they don't, and that fails. Similarly, the manipulation attacks we find against Quick are detected when we end up with different initial encryption keys during the handshake. Unfortunately for Quick, SSL and TLS consider this hash failure to be a fatal error and immediately quickly terminate that connection. In Quick, this failure to decrypt is not considered a fatal error, and as a result, the protocol doesn't terminate the connection quickly, and we have to wait for this connection timeout before these connections terminate. We did look at some mitigations for these attacks. Unfortunately, mitigating replay attacks seems to be pretty much impossible without limiting these public cacheable parameters like the server config to a single use. But of course, doing that prevents 0 RTT connections, which is, of course, one of Quick's major features. For packet manipulation attacks, the situation is a little bit more hopeful. We could sign all of these modifiable parameters that contribute to the encryption keys, but this introduces additional signature-related computation and overhead, which is actually also a source of denial of service because attacker can spoof a large number of these connection requests, which require signature verification. Okay, so at this point then, we've talked about our provable security analysis. We've talked about the performance degradation attacks we found. I'd like to spend just a couple minutes talking about recent related work on TLS 1.3. In case you're not familiar, TLS 1.3, next version of the TLS protocol, currently in draft stage. I think the current draft is like dash 14. Hopefully it becomes standardized here soon. Turns out TLS 1.3 actually has a number of similarities with Quick, including a handshake with multiple keys and a 0 RTT mode, very similar to Quick's. Also, very encouragingly, from a provable security perspective, we've already seen a number of provable security analyses for TLS 1.3, despite it still being in draft stage. So whereas for prior versions of TLS, it took something like 20 years from the initial development of SSL to having a provable security analysis. And here for Quick, we demonstrated a provable security analysis a couple years after deployment. Here for TLS 1.3, even before the standard is finally standardized, we have a lot of work being done and a number of provable security analyses already published, which is very encouraging work. Just to briefly talk about a couple of those, at CCS last October, there was a work that showed that the TLS 1.3 drafts are in fact secure multi-stage key agreement protocols, and showed how to compose them with symmetric key protocols to securely exchange data. And then just a couple months ago at IEEE Security and Privacy, there was a work that developed formal models for all of the TLS 1.3 handshakes. And there's a number, there's like a full handshake, a pre-shared key handshake, the zero RTT handshake, maybe a resumption handshake. I have to, don't remember precisely. And then they used some automated automated tools to prove the security of all of these handshakes. And then similarly, another work at that same conference showed that all of these handshake modes compose together securely in an arbitrary order. So TLS 1.3 doesn't have any of these multi-handshake attacks like we've seen against prior versions of TLS. Also, very interesting, so while provable security is very, very important, we also need to study the security of our implementations and the environments in which they're deployed. Another work from CCS last year demonstrated an attack based on the weaknesses of RSA-based PKCS encryption that results in attacks against TLS 1.3 and QUIC if they coexist with prior versions of TLS, and even though neither QUIC nor TLS 1.3 actually support PKCS. And basically this attack uses the prior versions of TLS to forge a signature that TLS 1.3 and QUIC accept, thereby breaking their security. So not only is provable security analysis is important, we also need to carefully study the environments and the implementations where we actually deploy these protocols. And that pretty much concludes my work here. Just as a brief summary, in this work we developed a security definition for performance-driven protocols like QUIC and proved that QUIC satisfies our definition of security. And then we discovered and implemented 5 different performance degradation attacks against QUIC, showing that they are in fact practical. That concludes my presentation. If you're interested in learning more here, I encourage you to check out our full paper at ePrint or off of the author's websites, which has all of our security definitions, proofs, and all details on the attacks. And with that, I'm happy to take questions.
Hi, Samuel. I'm Dave Blanco from Akamai. I read your paper before this,
okay.
and the presentation helped me understand it better. The thing that I'm curious about that you might help me in my work, and if it's too far afield from this, just explain to me why. I noticed in the paper it doesn't mention SNI, the server name indicator that we use to set up the initial encrypted session.
Yes.
And there's been work in the past in the IETF to try to encrypt that. And I'm less familiar with crypt than I am with TLS 1.3. But what I'm wondering is, obviously with the thing you described, you have this opportunity to send SNI encrypted under the subsequent sessions because you have this 0RTT already encrypted context.
Well, that's true, but you're also here, part of that server config, or logically part of that server config, is the SSL certificates and verification. So you still need that at the very beginning prior to setting up these encryption keys.
Okay, I think I understand that. And so this afternoon in TCP Inc., I'm going to propose a way that we can omit SNI for when we don't need it, because maybe you have a unique IP6 address for every service. And I was just wondering for your comments basically on how could we improve either with QUIC or apply techniques from it to either obscure or omit SNI.
So QUIC actually does send SNI. It's in clear text. It's abstracted out of the security analysis part of this work. I'm not sure I have any great suggestions for you, unfortunately.
It's out of the domain of what you're doing because it's really a privacy concern rather than a security concern, even though
Yes, and certainly for the security analysis part of it, it's completely abstracted out of this analysis. Yeah, not really in scope, unfortunately.
All right, thanks a lot.
Stuart Cheshire, Apple. One of the questions I was going to ask as I was watching the presentation is many times you mentioned TLS, and I was
Yes.
going to ask you, does that include TLS 1.3 with its zero round trip facilities? And then I saw towards the end you start mentioning TLS 1.3. So I'm curious to know, of the vulnerabilities you found, which ones are flaws in Quick specifically that TLS 1.3 doesn't have? Which ones are just inherent with any zero round trip protocol and they're kind of unavoidable? Because it'd be interesting to know if there are things that can be fixed in Quick, should that be done. You also commented that there have been some security analyses done of TLS 1.3, even though it's not final.
Yes.
And I would argue that doing that before it's final is exactly the right time to be finding the security flaws, before the RFC is published, not afterwards.
Absolutely, yes. So in terms of which of these attacks are applicable to TLS 1.3 or unique to Quick, I think most of these are essentially going to affect all types of zero RTT protocols. By caching that information, you're essentially giving it to the attacker to do these kind of replays against. One of the big things that TLS 1.3 could look at is some other way to provide to prevent IP spoofing, because as we see in a number of these attacks, that source address token that Quick uses is one of the major features here that we can leverage that provides some protection. So even the STK replay attack, right? It provides some protection against IP spoofing, but not complete protection. We can still replay it if we spoof the single IP address. Let's see. Something else I wanted to say there. Shoot.
Okay. Well, okay, thank you.
Yeah. Other questions?
Thank you. So I was so fascinated by these two talks that I totally forgot to put the blue sheets into circulation until the Great, then we'll be all early for lunch. The blue sheets, I think they're sort of in the third or fourth row, so if you want to do me a favor, come up and sign them. Thank you. See you in Korea. Oh, I should mention, we're going to start the call for nominations for the 2017 cycle of the ANRPs at some point soon. So we're going to open basically the nominations. I'm going to send out an email. If you go to conferences and you see papers that you think are as good or better than the ones you saw today, nominate the authors or convince them to self-nominate. We don't discriminate against self-nominations. In fact, we encourage it because so nobody other than me can tell whether it's a self-nomination, and I don't care, and so the section committee doesn't know. So if you're an author, nominate your work, right? And I think that's the last thing I forgot to say. Thank you.